Today, we're going to be walking through a derivation of the electromagnetic field tensor. Along with that, Trevor's also going to go through a pretty neat example comparing the electric and magnetic fields of a point charge in a rest frame and a co-moving frame. And this is pretty much just to illustrate that classically, only charges that move create a magnetic field, right, like current, whereas relativistically, the point charge could be stationary and an observer could be moving into that observer. It still looks like there's a magnetic field, which is pretty neat, but I'll let Trevor dive into that. Um, First off, in order to understand this derivation, we're going to have some background. So let's first talk about what a four vector is and how it is different from our ordinary vectors that we see in everyday physics. So a four vector is a concept that's used in the context of special relativity in spacetime, and it differs from your traditional vector in both structure and interpretation. So we see here our four vector has three spatial components and one time component. So we have this index mu here, and the zeroth component corresponds to the time component, and 1, 2, 3 usually correspond to x, y, and z. So we have these three space components and one time component, whereas your normal vector usually just has these three spatial components. The way they mostly differ is their dimensionality, which we just touched on, right? Their physical interpretations, what they represent, and their transformation properties. So three vectors, your ordinary vectors, transform according to Euclidean symmetry, so you can like rotate them and translate them. They'll be the same. Four vectors transform according to the Lorentz transformation, where the components of the four vector may change, but the space-time interval and what the book in your prep activity refers to as the invariant interval remains the same. Next up, we're going to have to talk about some tensors. So on the left here, we have a rank 0 tensor, which corresponds to a scalar. It's just a number. Over here, we now have an array of numbers, so we need an index mu to indicate which element of our array we're talking about. This is called a rank 1 tensor, and we call these vectors. Now we have two indices, which means we need two numbers to describe which element we're talking about in this array, which is called a matrix, and this is a rank 2 tensor. And over here, we have three indices. This is a rank 3 tensor. This is when we start calling them tensors, right? Getting a little bit more into the ranking. These are technically both rank 3 tensors, but we can go a little bit beyond that and describe this as a rank 3, 0 tensor. And this one is a rank 1, 2 tensor. We first indicate how many indices are in the top and how many are in the bottom. So for example, this would be a rank 3, 2 tensor. This would be a rank 0, 4 tensor. Now, if we go back, we might be wondering what's increasing with the rank of these tensors. And it might be easy to guess that maybe the dimensionality, right? Like a scalar is rank 0, it's in a zero-dimensional world. But we can clearly see that's not the case when we look at this rank 1 tensor, right? Usually these are corresponding to spatial components. So if we have an x, y, and z component, that's clearly three-dimensional, right? What's really increasing with the rank of tensors is the number of physical quantities that are used to describe the elements within them, right? So we have a rank 2 tensor. We have two physical quantities describing what's going on here. For example, a stress tensor is a rank 2 tensor. It uses two physical quantities in three-dimensional space to describe it, right? We describe them using force and area. Okay, now that we have this background, let's touch on the upper and lower indices, which is also touched on in the prep activity. But upper indices are called contravariant, and these are your things like positions, velocities, and directions. When you scale your coordinate system, these quantities scale the opposite way. For example, let's say like you're zooming in on a map, your contravariant components adjust the opposite way. So here, let's say you are at a physical position that is 3 kilometers east of the origin. If your grid lines were 1 kilometer each, then you'd be at a position of x equals 3. Whereas if you zoom in a little bit, your each grid line now corresponds to half a kilometer. So to be at the same physical position, 3 kilometers east, your position would now be described as x equals 6. Your lower indices are called covariant. These are things like gradients, like temperatures, pressures, slopes, and these scale the same way as your coordinate system, whereas contravariant scale the opposite way. So now that we have this kind of background on four vectors and tensors and indices, we can kind of dive into this electromagnetic field tensor. We're going to start off by using our four potential, our four gradients, and these two definitions from electromagnetism. In the prep activity, we looked a little bit at this four potential, and we saw that the time component of your four potential is really just your typical potential divided by the speed of light. And then the other quantities are your spatial components. So we went ahead and put a box around that. We're going to put a pin in it and come back to it from later. We're going to do the same thing for our four gradient. We're going to break it up into its components. But we see here we picked up a negative 1 over c. And the reason that's negative, the book also touches on this, but your covariant variables, if you have a covariant vector, the time component is negative, and if you have a contravariant vector, the time component is positive. But gradients are a little bit counterintuitive because a lower indice really corresponds to an upper indice in the denominator, whereas an upper indice, which is what we have here, corresponds to a lower indice in the denominator, which is where we pick up this negative sign. So that's why we have a factor of -1/c. And we chose this upper indice so that our field tensor in the end has two upper indices. So we put a box around these. We're going to come back to them later, and now we're going to take a look at these definitions from electromagnetism. So we're going to take our electric field and we're going to break it up into its components, right? This gradient can be broken up into its x, y, and z component, as well as this time derivative for the different components of our potential. So that's what we've done here on the left. And on the right, we've expanded our magnetic field by using the definition of the curl. Go through the steps here, and we've also rewritten our magnetic field components. So now we have our 4 potential rewritten, our 4 gradient rewritten, and all the equations for different components of the electric and magnetic field. And what our goal here is we want to write the components of the electromagnetic fields in terms of the 4 gradient and the 4 potential. So to do this, we're first going to look at the x component of the electric field. And we're going to say, okay, well, this v really just looks like the 0th element of our 4 potential. And this x, this ax, really just looks like the first element of our 4 potential. So we're going to go ahead and substitute those in. And keep in mind that this v is really missing a factor of c. So we're going to count for that when we sub it in here. And I tried to keep it color coordinated. It's a little hard to see. But now here's our new expression in terms of the 4 potential. And now if we take a close look, we see that this d by dx really just looks like the first element of the 4 gradient. This d by dt looks like the 0th element, again, missing a factor of c. So we go ahead and substitute those in, and now we have a final expression for the x component of the electric field, only in terms of the 4 gradient and the 4 potential. Now we go through the same procedure for the y and the z components, and these are the answers that we get. Now we're going to do the same exact thing for the magnetic field components. We look here, we see that this is really just the third element of the 4 potential, and this is really just the second element. This d by dy is the second, or the third element, no, the second element, sorry, of the 4 gradient, and this d by dz is really the fourth, not the fourth, the third element. So we go ahead and substitute those in, do the same procedure for the y and the z components, and we have these equations. So now we're going to combine all of this together. We have all of these equations. And what's really neat here is we've written the electric field and the magnetic field in terms of just the 4 gradient and the 4 potential. Now, if we think back to the beginning of this, what can we do if we only need 2 physical quantities to describe all these equations? We can put them into a rank 2 tensor, 4-dimensional rank 2 tensor, which is a matrix. So I've gone ahead in the next slide and I've rearranged all the electric field equations, moved c to the other side so that they all take on the same form here. And I've also solved for the negative y component of the magnetic field, and we'll see why here in a second. So if we take a close look at this, we see a pattern here, right? We see 0, 1, 1, 0, then see 0, 2, 2, 0, 0, 3, 3, 0, 2, 3, 3, 1, right? We see this pattern. So we can generalize this. We can say d mu a nu minus d nu a mu equals f mu nu, which this just corresponds to the element of our matrix, our rank 2 tensor. So this corresponds to the 0, 1 element. So we went ahead and put this ex over c and that 0, 1 element. Same thing here, 0, 2, 0, 3. And the reason why I solved for a negative y component of the electric field is so that we could fill out the top half of this matrix first. We can quickly see that the diagonals are all going to be 0. And this is an anti-symmetric matrix. If we try to solve for the 1, 0 component, we quickly see that it's really just the negative of the 0, 1 component. So then that quickly allows us to fill in the bottom half of this matrix, and notice how the y component of the magnetic field is now positive over here. So that is pretty much the nitty-gritty of constructing the field tensor. It's really neat finding that we can put the magnetic field and the electric field into one tensor that describes how they both work. And we were able to do that by rewriting them in terms of 2 physical quantities corresponding to a rank 2 tensor. And now Trevor is going to go through the example of actually using this field tensor, and how that's pretty cool.
So now that Natalie has derived the field tensor for us, we can start putting it into practice a little bit and seeing how it's helpful in order to see how the electric and magnetic fields change in different frames of reference. So we know that the Lorentz transform only applies to 4 vectors because you need the time component as well as the spatial components. So since the electric and magnetic fields aren't 4 vectors separately, the electromagnetic field strength tensor allows us to see how they transform from one inertial frame to another using Lorentz transform. So I have this problem here that I wanted to just go through really quick just to see kind of how this would be applied. And so we're looking at a point charge, which is at rest in an inertial frame S prime. A sensor moves with a constant velocity in the negative x direction with a co-moving inertial frame S. What is the electromagnetic field strength, or what is the electromagnetic field in the co-moving frame? And so we can see that we need to find what the transformation like rules are for the Lorentz boost that we're performing, which is in the positive x direction. And because we're moving from the rest frame S prime to the co-moving frame of the sensor S, which is, since the sensor is moving in the negative x direction, then we would be boosting in the positive x direction in order to go from S prime to S. And so between inertial frames, the field strength tensor would be transforming in the same manner as the coordinate 4-vector. In this case, we're talking about x mu, which is the 4-vector in the x direction. And so from x mu to x mu prime, we're looking at using the Lorentz transformation matrix in 4 dimensions, which has 2 indices, mu and nu, and that's acting on x nu. So x prime mu equals lambda mu nu x nu. And in the same manner, we have F mu nu, which is the electromagnetic field strength tensor, and transforming it to F mu nu prime, which in this case, you have to do the Lorentz transformation twice or apply the matrix twice because of the 2 indices, since F mu nu is a rank 3 tensor and X nu is a rank 2 tensor. And so rearranging this using matrix rules, I'm not going to go over that super much. It's just some linear algebra stuff. But essentially, because the Lorentz transformation matrix is symmetric, we can rearrange the indices a little bit here to show that F mu nu prime is equal to lambda F lambda transpose mu nu. And so this is the Lorentz transformation matrix in 4 dimensions, just to go over that in case that is not readily available information. This is very simple stuff. I mean, we learned this in special relativity, or I guess theoretical mechanics at OSU. And so this should be pretty familiar to most people. And so now we'll be performing the boost using the previous equation that we found. There's a lot of matrix algebra, so I'm not going to really go over every step, but at the end we have that F prime is equal to this whole matrix here at the bottom. And then relating the quantities in the F matrix to the quantities in the F prime matrix, we can get our transformation rules from F prime to F, which in this case would be E prime is, or EX prime is equal to EX, BX prime is equal to BX. And then these are the quantities for EY prime and EZ prime, as well as BY prime and BZ prime. And again, this is just coming straight out of the matrices, comparing, for example, in F, the index 0, 1 would be EX of C, or EX over C. And in F prime, the index 0, 1 is also EX over C. And then you can see that in 0, 2, that quantity versus the quantity in F 0, 2, you can just set those equal to each other and solve for the E prime. And so then in our situation, what we want is the transformation rules from E to E prime and B to B prime instead of the other way around, because what we're looking for is the electric magnetic field in the co-moving frame, which is S and not S prime. And so what we're looking at is what we, just to make it simple, is from the rest frames perspective, we could do some math there, and that should tell us how to get to the co-moving frames perspective. And so from the rest frame, the co-moving frame is moving with a negative velocity in the x direction. And so we can switch the primed and unprimed quantities in the earlier transformation rules and then change the sign of V, which would match our situation. And so we want the to do the math in the rest frame because it just makes it easier to do a lot of these calculations. Like we know that the magnetic field in the rest frame will be 0, all the components, and then the electric field will be just calculated using Coulomb's law. And so we have here that E vector prime is equal, or with respect to T prime and R vector prime is equal to just the classic Q over 4 pi f naught times R vector prime over the magnitude of R vector prime cubed. And then these are the components I laid out here. They're all very similar, except just having X prime, Y prime, and Z prime respectively in the numerators. And we know, like I said at the bottom, that the magnetic field components will all equal 0 since the charges at rest in this frame being S prime, just to clarify. Then we also have to remember to change our coordinate basis in order to make all the math work out. And so we can also, arising from the transformation rules we had before, know that T prime is equal to gamma times the quantity T minus V over C squared X. X prime is equal to gamma times the quantity X minus VT. And then Y prime and Z prime are both equal to their unprimed quantities. And so just plugging in what we got for the primed components of the electric field into the transformation rules, which I've shown here on the left, you can see that these are the components of the electric field in the co-moving frame or the sensors frame. And there is not really much different from the form that it had when we were using Coulomb's law, except for this factor of gamma squared times the quantity X minus VT squared in the denominator of all of these components. And what this is essentially achieving is that the X minus VT squared will squish the electric field lines in the direction of motion. So if you have like pick some time t and center a sphere on that point in time, then traveling towards the poles, the electric field lines will be spaced farther apart, and then towards the equator, the electric field lines will be spaced closer together as the charge moves. And the interesting thing here is that the components of the magnetic field in the co-moving frame are actually non-zero. I mean, except for the X component, but we don't care about the X. And so you can see that the Y and Z components of the electric field or magnetic field in the co-moving frame are non-zero and are proportional to negative Z in the Y direction and Y in the Z direction, which, if you remember, corresponds to a counterclockwise rotation around the X-axis. And so what this is essentially telling us is that when the charge, or I guess the sensor in this case, is moving in the negative X direction, from its point of view, the charge, which is at rest in the lab frame, so to speak, is actually moving in the positive X direction from the sensor's point of view. And so it detects a magnetic field from the charge as if the charge were moving in the positive X direction, when from our point of view, it's not moving at all. And so the cool thing about this is that it agrees with the Biot-Savart law, which we've used a lot in this class, with the right-hand rule. And you can see that in this diagram, the right-hand rule is telling us that if there's a current or a moving charge or charge distribution in the positive X direction, if we're saying the positive X direction is the right, then in the Z direction, you're moving negative Y, or positive Y, sorry, my bad. And in the Y direction, which would be out of the screen, you're moving negative Z, which is a counterclockwise rotation, which agrees with this rule. And so it's more so that, not that the Biot-Savart law and relativity just happen to agree, but more so that the Biot-Savart law actually arises out of special relativity, because the magnetic field that's generated is not just generated whenever you agree that the charge is moving in general, because it's not universal due to relativity. And so even if a charge is at rest in one frame, if it's moving in another frame, then anyone that is observing from that frame will detect a magnetic field from the charge. Thank you.